Okay, so that was all the theory. Now let's actually put some numbers in here and see if we can make sense of this. Sometimes talking in general theoretical terms doesn't really cause things to fall into place for people once you get a chance to actually start to move some numbers around. Things make a little more sense. I know that's certainly the way my brain seems to work. So I've posted an exercise sheet, and this is one of the questions from it we're going to do. So it's exercise sheet 1007-7A. So we're on the first page of handout number 7, and we're going to look at question 3. So the first question is really pretty straightforward. Second question, I thought the numbers weren't really where I wanted them to be for us to get through our conversation. So let's do question 3 together. What I've got here, so first of all, this top half, this is kind of like what you see in the exercise sheet, right? It's a table, and you've got to fill in the blanks on the table. In order to accomplish that, though, you're going to have to draw the 3 triangles. So I've got them here as well. Unfortunately, if I was in a classroom and I had 3 or 4 whiteboards, I'd do all the math, every calculation, every step along the way. I think what I'm going to ask you to do is probably hit pause many, many times as we go along. I'm going to identify the next step, and then you stop it, try to do the math, see if you can come up with the right answer. And then I've got the numbers in front of me. I'll just keep filling them in. And really, it'll be about understanding the process, how we can get from point A to point B to point C through the circuit. Okay, so let's look at what we have. So it's a series RC circuit. So we have a resistor and we have a capacitor that are connected in series in our circuit. Now, I'm actually going to just take an aside here for a second and say that practically we never connect loads in series. Okay, I think probably Pete had this conversation with you last term. We do the math of resistors connected in series, but typically, practically, we always hook everything up in parallel because everything gets the same voltage that way. So same is true when we move into AC circuits. Realistically, we would not take a resistor and a capacitor and connect them in series. Most likely we would connect them in parallel. But it's important to do this math because Pete also mentioned a couple of weeks ago that there is definitely internal resistance within the capacitor. And we can do the math on that by pulling them apart and pretending that they're 2 separate loads connected in series in the circuit. And so that's exactly, practically, the math that we're doing here. Okay? But we can call that the internal resistance of the capacitor, or we can say that that is a resistor connected in series with the capacitor. The math is the same. Whichever way is more comfortable for you to think about it is fine. I will refer to it as a resistor connected in series with the capacitor just because that's really how everything's going to fall into place. Okay? But you can think about it differently in terms of practical application. Okay, but that's what we have. We have a resistor connected in series with a capacitor with an AC power supply. So the handout shows a table, okay, and you have the first column is all your total values. So these are the numbers at the power supply, okay. So total impedance is Z, total current. The applied voltage, or we could call that total voltage. Okay, it's the same thing. All right, these are the totals. Okay, second column is all of your resistive values. What is the size of your resistor? Current through the resistor, voltage drop across the resistor, and this is our true power. And then the capacitive numbers are over here. Now, the other thing that I want to show you to help you understand is how does that relate to our triangles? Well, look at this. All of our total values, these are the hypotenuse of each of our triangles. Okay, the apparent power is the hypotenuse of our power triangle. EA is the applied voltage, is the hypotenuse of the voltage triangle. The totals, okay, we've listed them here, but, sorry, the current, sorry, is what I meant to say. The currents, what can we say about currents in a series circuit? They are the same, whether we talk about the total current, whether we talk about the current flowing through that resistor, whether we talk about the current flowing through that capacitor. Okay, current is always the same. Okay, so we have them listed here. Once we calculate it once, we can fill in all 3 of these because they're the same number. We don't need to draw a triangle. In fact, it's that number that helped us build the triangles. And then finally, our impedances. So Z is the hypotenuse of our impedance triangle. Same thing here with the resistances, in the sense that this represents one side of each or all of our triangles. So the resistive values are what side of our triangles? Well, here's our angle theta, and so the resistive values are always going to be at the 0 degrees, that horizontal vector, and that is the adjacent of our right angle triangles. So all of our resistive values, the power, the voltage, and the resistance or the impedance, all of those are the adjacent of our triangle. And so the capacitive portion of the circuit, these values are always the opposite of each of our three triangles. So we can relate numbers back and forth from one to the other. Okay, now one final thought before we finally get into the numbers. I can apply Ohm's law to calculate values as long as I stay within one column on our table, or as long as I look across at the same side of the triangle. Okay, I can use Ohm's law to calculate Z when I know EA and once I figured out what I is. I don't know I yet, but once I find my current, then I can use Ohm's law to use this 220 volts, which is my applied voltage, to find the total impedance of my circuit. I can use Ohm's law as long as I stick to the same side of the triangle. Okay, I can't use current and EA to find R or to find XC. Okay, it's just not going to work. All right, Ohm's law here or here or here. I can't mix and match. Okay, and so that's how we're going to start finding numbers and filling in blanks, is using Ohm's law in that fashion. Okay, we don't have, you can see here on the table, we have one value in each column, so Ohm's law is not going to be helpful initially. Okay, the other set of tools that we have are the things that we know about right angle triangles. So we can use sine, cos, tan, and the Pythagorean theorem to work a triangle. Okay, and so in terms of equations, that's just about the end of the conversation. Okay, Pete's already shown you tons of equations. We referenced in one of our meetings a couple of weeks ago about the very back of the Delmar text having pages and pages and pages of equations, all of them valid to be sure, but they come down to just that. Okay, Ohm's law, or the power equation, right? To get over into the power triangle, it's volts times amps equals watts, or whatever units we're talking about. We've got Ohm's law, we've got the power equation. Okay, those are the two equations we can use within a column. And then we've got SOHCAHTOA and Pythagoras. Okay, and everything builds from that very small collection of equations. Just always ensuring that we're using the right variables. Okay, enough talk. Let's get into the numbers. Where do we start? While I've been going on and on and on, you've been staring at this and hopefully asking yourself, where to begin? Okay, so I already mentioned that we can't use Ohm's law because we don't have a pair of values in any given column. So where do we have two values so that we can find more? Because that's the same rule that we need when dealing with a triangle, right? You know, two things, we can find the third thing. All right, so where do we have that? I immediately see that we have that here in our impedance triangle. We know the adjacent and we know the opposite. All right, we have a value for R, so this is a 10 ohm resistor. We know the value for XC, so the impedance, the reactance of our capacitor happens to be 35 ohms. And so with those two pieces of information, we can find the third. So here's where we're going to pause the video and apply what equation? The Pythagorean theorem. And using that, we can find the value for Z. And I'm just going to cheat. The value for Z is 36.4 ohms. So the Pythagorean theorem allowed us to determine that. Okay? So we can see, I just drew the triangles. If we wanted to be more accurate, what would the triangle look like? So the hypotenuse is the longest side, okay, but it's really not very much longer than XC. So I'm going to draw it in this space for a second. We'll have to erase it fairly quickly. But that triangle actually looks like that, doesn't it? And so once we get to the point of calculating for the angle theta, what can we expect to find? What is that number going to be? We can guess, all right, just throw an estimate out here for the time being. I'm going to say maybe 85 degrees. Okay, I don't know if that's right. Maybe it's 75 degrees. Maybe it's 89 degrees. All right, but it's going to be a big number. It's going to be up there approaching 90 degrees because that's a really, really significant angle in terms of the shape that that triangle is going to take. Okay, so that sort of thought process is always beneficial as you enter this to try to understand what it is you're going to see. Okay, that's the kind of angle we're actually looking at. That's what that triangle really looks like. Okay, so now what can we do? 36.4 ohms is the value for Z. 36.4 ohms is the value for Z. Okay, which means I can use Ohm's law, right? I know the hypotenuse of my impedance triangle. I know the hypotenuse of my voltage triangle. I can use those values to calculate current. And I see it right here. I have voltage, I have impedance, I can calculate current. So we'll use Ohm's law. So I equals E over R. So here's, I'm sorry, another tangent. Here we go. We know that Ohm's law, I equals E over R. Okay, so all we have to do is make sure we use the right variables to calculate for IT. Okay, so IT equals, it's actually EA, the applied voltage, over, and it's not R at all. Okay, specifically it is Z. So there's an equation that you might find listed in the back of the Delmar. IT equals EA over Z. All right, but it is simply Ohm's law using the correct variables to stay within our totals column. Okay, so based on that, you've now paused the video, done the math, and determined that IT equals 6.04 amps. Okay, and now because it's a series circuit, because I is constant throughout, we can take that number and move it here, 6.04 amps, and move it over here, 6.04 amps. And see how easy this gets now? Ohm's law, we know IR, we know R, we can calculate ER, right? So voltage equals I times R, so 6.04 times 10, I don't even have to check my notes for this, 60.4 volts, and over here, 6.04 amps times 35 ohms, I need to check my notes for this one, this is EC, and EC equals 211.54. So let's put these numbers down here. 60.4 volts and 211.54 volts. Okay, let's check our numbers. 211.5 is just a little bit less than 220. So the opposite is just a little less than the hypotenuse, which was the same relationship we saw over here in the impedance triangle. Okay, the opposite is just a little less than the hypotenuse. So it looks good because we know this angle, whatever it happens to be, is going to be the same in all three triangles, right? So this kind of a relationship, we want to look for it, we want to see it, we know we're on the right track. Okay? Now we can use the power equation, power equals E times I, and there it is, staying within the same column, so 60.4 times 6.04 means the true power is 365.3. 365.3 watt. This is watts, right? This is true power. This is the actual work being done by the circuit, okay? As opposed to reactive power, same thing, volts times amps. What is this number? It is 1278.5. 1278.5. And what's the units on this? This is VARs, volts, amps, reactive. So remember what this is. This is energy being stored in the capacitor. Okay, it gets stored and released as that capacitor charges and discharges throughout the AC sine wave. Okay, but it doesn't really do anything. It's power that's being dissipated, but it's not doing any work. This, the resistor, is where the work is done in the circuit. Okay, it's generating heat. Okay, that is the circuit's output in terms of its work. So let's go back here to apparent power. That is the hypotenuse of the power triangle, which means it's going to be, we've already seen the relationship. We know that the hypotenuse is just a little bit more than the opposite. And so the opposite was found to be 1278. So this is going to be 13 or 1400 maybe. Let's see. 1329.7. 1329.7. And this is volt amps. Okay. So this is the demand on the power supply. This is how hard that power supply has to work to provide power to the circuit. That's the power demanded by the circuit. But that's the power output, useful power output in the circuit. Okay, so we can say and we can see that the circuit is very inefficient. All right, the apparent power, 1329.7 volt amps. That's the demand on the power supply, but true power is 365.3 watts. That's the actual output of the circuit. Okay, so it's not a very efficient circuit. And we saw that when I drew the triangle. When we know the circuit actually looks like this, okay, that's certainly not an efficient circuit. The hypotenuse is the demand on the power supply, and the adjacent is the work being done by the circuit, the heat being generated by the resistor. So what is this angle? Well, we've got all kinds of choices here. Okay, now that we have all of our sides in all three triangles, literally pick two. Okay, sine, cos, or tan, based on a couple of the appropriate numbers. So pause the video, try it, use a couple different spots. All right, use sine with the impedance triangle, use cos with the voltage triangle. Get creative. Okay, try all kinds of stuff. Okay, and now I will tell you that that angle right there is 74 degrees. 74 degrees. It's actually 74.05. 74 degrees, we'll round it to that number for the purpose of our conversation. So I was estimating 85, but I did admit that maybe it's only 75. There it is. Okay. So that's the angle, which then ultimately brings us to the final point, which is the power factor, right? That's really the thing that we want to calculate here. What is the power factor in our circuit? And so the power factor speaks to that efficiency that I was talking about, the relationship between the power demanded of the power supply as opposed to the power output in a useful form by the circuit, okay? And since we have a really large angle, which we call a really inefficient circuit, we're going to have a power factor that's very small. So the power factor is going to be somewhere between 0 and 1. 0 meaning that our angle theta is 90 degrees and there is no useful power output whatsoever. And 90 degrees meaning that, the power factor of 1 means we have an angle of 0. Okay, it's strictly a resistive circuit. Okay, if there is no capacitor, if there is no inductor in the circuit, it's purely resistive. The voltage and current are in phase. There's no triangle. That would result in a power factor of 1. Okay, so the power factor is always going to be between 0 and 1, and a lower number equals a more inefficient circuit like we have here. And the number we have for our power factor is 0.2747. Sorry, I got ahead of myself. How did we calculate that? Okay, power factor is the true power divided by the apparent power. So what is this relationship? Okay, and this is why we'll always have a power factor between 0 and 1, because the adjacent can never be a bigger number than the hypotenuse, right? So it'll always be some kind of fraction. We could also calculate that back here in the voltage. We have ER, the voltage triangle, ER over EA. And back here in the impedance triangle, it is R over Z. So any one of those will provide us with the power factor, which we determine to be 0.2747. Now, Finally, what is the adjacent divided by the hypotenuse? Well, the adjacent divided by the hypotenuse is cos, right? The cos of the angle theta equals the adjacent over the hypotenuse. And so what we're talking about here is the cos of the angle theta. And we can use that to calculate our power factor. Okay? And that's it, guys. That's really how you go about doing this. And the trick is to keep it all straight. Okay? Use Ohm's law within columns, move from one column to another using the triangles and SOHCAHTOA and Pythagoras. And I knew there was one final thing. The power factor must be either leading or lagging. Okay, so I've already spoke to this concept in previous videos. In an RL circuit where we have an inductive load, we have a lagging power factor because the current lags the voltage. Now, because this is a capacitive circuit, we have a leading power factor because the current leads the voltage.